Yeah, thanks for having me here. So, as Prateek said, the title is extremely long, and that's because all three of us, Phil, Rocco, and I, have great imagination, so that's why we came up with this title. Anyway, I'll discuss the title over the course of the talk. This talk is about one of the most basic tasks in unsupervised learning, that of learning a probability distribution from random examples. Kind of distribution we'll be interested in this talk are discrete probability distributions. Okay, so the rest of the talk, basically I'm going to first start by formalizing what I mean by learning a discrete probability distribution, survey some prior work, define the problem we are interested in, hopefully tell you about our results, and hopefully some of the ideas that underlie the results. And I have way too many slides for 40 minutes, so there's no way I'll go through the whole thing, so feel free to stop me. So there's no set of things I need to cover. Okay, so as I said, learning probability distributions motivated by several kinds of applications in machine learning is one of the most fundamental unsupervised learning tasks. So think about all these kinds of models that we have seen in this meeting so far, like Gaussian mixture models or things Piyush talked about yesterday, or models like Markov random fields, determinantal point processes. These are all examples of learning probability distributions from examples. And typically motivated by the applications, these are probability distributions which are typically high dimensional, sometimes continuous, sometimes discrete, and so on. But in this talk, what I'm going to do is that I'm going to take a more complexity theoretic take on this problem. And we're going to basically look at problems which are probability distributions which are in some sense generated by a computationally very simple process. Okay, I'm going to define the process. And what we're going to see is that some very interesting phenomenon on sample complexity is going to emerge. So what I want you to keep in mind is the following. For learning of Boolean functions, there is a very simple, well-known notion of VC dimension, a very simply defined combinatorial notion, which exactly captures the sample complexity of the learning problem. If you're thinking about learning Boolean functions, which means like supervised learning, so classifications. And that is why typically we are only focused on the computational complexity, because the sample complexity is like super well understood in most cases. Unfortunately, for learning distributions, no such analogous characterization is known, something like a VC dimension which exactly captures the sample complexity. And one of the things that I feel at the end of this work, it's not like a scientific statement, but I feel at the end of this talk, will see, and I feel like I have good reasons to believe that there may not be such a nice characterization of sample complexity for learning distributions. Okay? So let's start with the problem. Okay. So first, what is the kind of things we're interested in? We are interested in learnability of discrete distributions. For us, discrete distributions will just be distributions over integers. And as is usual, a learning problem is characterized by a class C of distributions. And this class C is known to the learner. Whereas an instance of the problem, there is an unknown target distribution D belonging to C. The D is not known to the learner, but C is. What learner does get are IID draws, so independent identically drawn draws from the distribution D. And the aim is that with high probability, let's say 90%, the learner intends to produce a hypothesis distribution D prime such that D and D prime are close to each other in L1 or total variation, whatever you want to call it, total variation distance or statistical distance. And so let's say we want to produce a hypothesis which is 1/10 close. Okay? And this task is sometimes referred to in statistics as density estimation, because all you're interested in is producing a hypothesis D prime whose density or whose PDF is close to D. So you're not insisting on D prime belonging to the same class C that you started out with, or trying to learn a parameter, learn the parameters if C happens to be a parametric class or anything like that. You just want to produce some hypothesis distribution D prime which is close to D. Is the general motive clear? And the natural question one can ask is, what classes of distributions can be learned efficiently? And by efficiently, we'll typically focus on two parameters: fast running time and hopefully few examples. Yeah. No, so I'm not insisting on D belonging to class C. It can be anything. It should be something like, small circuit, maybe. So let's start with the most basic case here, okay? Just to get started. So think of the class C to be Bernoulli random variables. So all distributions which are supported on 0, 1. Okay? So this is equivalent to learning the bias of an unknown coin. You're trying to just learn the bias of an unknown coin. Okay? And what you have access to are IID coin tosses of this coin. And it's kind of easy to see and well known that if you sample, if you shoot for any error parameter epsilon, if you toss the coin about 1 over epsilon squared times, that is enough to learn the bias up to error epsilon. And in most regimes of parameter, you cannot do really much better than 1 over epsilon squared. This is essentially tight as well. Maybe a little more complicated, but not significantly more, is if instead of thinking about the class C of distributions which are supported on 0, 1, let's think of the class of distributions supported on 0, 1 to n. Okay, still a very discrete, easy set. And again here, you can do the same thing. And it's well known that if you take n over epsilon square examples, you can, so if the class C of distributions consists of all distributions supported on 1 to n, it suffices to take about n over epsilon square examples. And these many examples are also essentially necessary to learn such a distribution, an unknown distribution over this domain. Okay? And both these examples are what one should call a brute force method. And by brute force, I just mean that the algorithms in both these cases is basically the empirical estimator, meaning you just take a sufficiently large number of samples, and then for every point x, you say the density is the empirical fraction of times it appears in your sample. And this works in the last two cases, in the previous two cases we have seen. So maybe let's take as a last example before we get started, maybe take an example where a non-empirical estimator does not work. And so let's focus on this class C, which consists of all distributions supported on 1 to n, except where the PDF is monotone non-increasing, meaning the PDF, is going down or never goes up. Okay? In this case, actually it turns out that you can do much better than the last setting. Instead of requiring n over epsilon square samples, you can actually learn this distribution with log n over epsilon cube samples. So you exponentially save in the factor of the domain size. And again, in many regimes of parameters, this log n over, you cannot beat this log n over epsilon cube. The second thing I would like to point out is that A, it's not an empirical estimator. And second, this kind of example is, it's a non-trivial estimator. It's a non-trivial learning algorithm in the sense, this kind of sample complexity you do not get by just showing that, there are only 2 to the log n over epsilon. There is an epsilon net of size 2 to the log n over epsilon cube, and hence you get these many samples. That's not true. If you want to cover the space of all monotone distributions over n, it's still like 2 to the n. So it's smarter than it actually requires an algorithm. It's smarter than that. Okay. And one more thing I would like to say is that I keep talking about sample complexity and not the time complexity. But for every example I'm going to talk about in this talk, the sample complexity, the way we are going to prove the bounds are algorithmic themselves. So I'm just going to focus on the sample complexity because the time complexity is going to be a marginal overhead. Yeah.